Hello, Geology students. We are back again today to talk about weathering and erosion. So I want to get started by talking to you again about the rock cycle. So you'll remember that we started our discussion with igneous rocks, and that's because igneous rocks originate at the mantle plume. So you have a body of magma that's coming up to the surface, and it will crystallize intrusively or extrusively. So what happens if that body of extrusive igneous magma is exposed at the Earth's surface? Well, it's going to go through a process that's called weathering and erosion. And in fact, you need weathering and erosion to produce a sedimentary rock. So a sedimentary rock that we'll discuss in future lectures is built of small particles that are formed through weathering and erosion. So I wanted to take some time to define what those terms meant. And when we look at the classic definition, we say destructive processes that alters the physical and chemical characteristic of a rock at or near the surface. So we're destructing it, and we're either destructing it either physically or chemically. And really what we're going to learn is that those two processes really happen hand in hand and can exacerbate one from the other. You will be familiar now with the Bowen's reaction series. And the Bowen's reaction series we used when we talked about igneous rocks, and we looked at the crystallization of different types of minerals out of a body of magma. And so what we said was the magma at depth could be about 1400 degrees C, and as it approaches the surface, it begins to cool. And as it does, these different minerals crystallize. So when we look at a body of granite, for example, we now understand that granite has three minerals: biotite, orthoclase or feldspar, and quartz. And when we look at Bowen's reaction series, we see that they crystallize at different temperatures. So biotite crystallizes at 1100 degrees, orthoclase at 1000, and then quartz at about 800 degrees Celsius. So we can use Bowen's reaction series then to also describe patterns of instability at the Earth's surface. So when we look at the crystallization process of minerals, we can also look at that as how they would be destructive. So certainly, if you heat a body of magma up to above 400 degrees C, olivine is going to melt. But we can also look at the instability of these. So if we have biotite, orthoclase, and quartz in a body of granite, the first one that's going to disintegrate is going to be the biotite. And you'll remember looking at that in lab, and it was a mineral that was really, really a thin sheet. So it's easily friable and easy to break into pieces. So you're imagining that will disintegrate first, followed by potassium feldspar, and then the very last thing that would be out of that body of granite would be quartz. And so when you consider your beaches, especially your East Coast beaches, Myrtle Beach, PCB, the sand that's present there is pretty uniform, so it's all one color, and it's mostly quartz. So the continental crust that we talked about is granitic, and as that continental crust goes through the weathering process, biotite and orthoclase weather out first, and so then you're left with quartz, and that's transported to the beach faces. So down gradient from the Appalachians in the case of the East Coast. So you have quartz being the primary mineral that's left, but we also see weathering at a variety of different types of scales. So whether that's a regional scale, looking at the decomposition of mountains, but we can also look at it from the purpose of like infrastructure. And that's what I show you here. So you're seeing some limestone tombstones that were often used in the 18 and 1900s because it was abundant, especially in a place like Georgia. But what we find is that limestone is really soft and can very easily be eroded and destructive. So it's not so much used anymore as building material. But we can look at bigger pictures. And so here on the screen is a picture of the Grand Canyon. And certainly over the past millions of years, we can see how the Colorado River carved the Grand Canyon. So a very large scale type of weathering pattern that we could see at the Grand Canyon. We could see in Utah at the Arches National Park, where it's mostly wind erosion. And then we could see it in a glacial national park, so up in Alaska. And then one of my favorite parks is probably the Badlands, and so the Badlands are in both North Dakota and South Dakota. And when you look at these landscapes, although they appear to be hard, they're actually quite soft. And so it's just amazing that this kaolin deposit, kaolin is a type of clay, is still present from the Eocene, so more than 30 million years ago. So two terms are often used. We often use the term weathering and we use the term erosion. And I wanted to define how those are different. So weathering, when we use the term weathering, weathering is a physical or chemical breakdown of a rock, while erosion is the transport of those pieces of sediment. So the term weathering is the physical breakdown of the rock, and then the process of erosion is explaining how those little pieces of sediment are transported from one location to the other. So when we use the term sediment, sediment can be applied to a wide range of different sizes. And we can ask a question about how sediment is transported, but the transport is largely going to be defined upon how big it is. So on the screen here, and this is super important to a geologist, we can define something that's very small to be a clay-sized particle, followed by silt, and sometimes those are termed mud. So like the Georgia red clay around here is going to be very small in diameter. So again, we're thinking of the individual pieces of that sediment that's stuck together, followed by sand, and then followed by things that are much bigger called gravel. So you can classify them as pebble, cobbles, or boulder. And when we look at sedimentary rocks, one way that we define them is by looking at their grain size. So different than an igneous rock, where we're looking at its texture, aphanitic, phaneritic, glassy. Here we're looking at the size and shape of the grain sizes. They can be really, really small, or they can be quite big. So one thing that we like to figure out then is how sediment is transported, and it can be transported by three different systems. So it can be transported by wind, by water, and by ice. And that's what we saw in the landscape photographs that we started this lecture with. So I showed you Glacier National Park, I showed you the Grand Canyon, and I showed you the Badlands in North and South Dakota. So each of those three systems formed depending on the transport of energy that was present. And so we can classify these systems, and we like to do this when we're a geologist, in terms of how much energy stored that they have. So sometimes that's challenging to do because there's always exceptions. So if you have a major flooding event, for example, or if you have a hurricane that brings a lot of wind. But considering all things equal, we would say that ice has the most stored energy. And so you're thinking about ice moving from high gradient down to low gradient. It's carving a valley. There's a U-shaped valley that will be there long after the glacier has melted. And as you see in this picture, in going towards eastern Colorado, you see these massive boulders. And so those are called glacial erratics. So you're imagining 26,000 years ago, the Laurentide ice sheet works its way down through Colorado into the great state of Nebraska. And then as it's doing that, it's breaking down the bedrock that's beneath it. It's entraining these massive boulders that can be larger than a house. And then as that glacier melts, it doesn't carry that sediment back with it. It leaves it in position. So these are called glacial erratics because as you can see around it, there's nothing that's like it. And so often if you're cruising through Nebraska on Highway 80 going towards Colorado, you'll see this giant boulder in the middle of nowhere and you ask, like, how did it get there? But it got there from the energy of a glacier as it was moving from high gradient to low gradient. We can also talk about dune systems that have to deal with wind. If you're interested in this type of landscape feature stuff, please take my geomorphology class, which has to do with landscapes and how landscapes change over time. It's pretty fascinating stuff, and it really gives you a good perspective of the world as you travel. So I hope you consider that. It's called Geo 360. So sand dunes are another example. So you're considering these tiny, tiny pieces of sediment, but as they're picked up and carried by the wind, they can build these giant structures. I've been lucky enough to fly over the Sahara Desert, and it's spectacular in the size and scope of these major features. So wind can also have energy to transport sand-sized particles, so much smaller particles than we would consider a glacier. But then we can also consider water. And so the Grand Canyon was carved by the Colorado River eroding through it. And so, that's just at normal conditions. At flooding conditions, water, of course, can have even more energy. If we think in terms of a tsunami, it can have maybe even more energy. So the moral of the story is that we like to make comparisons between weathering. So weathering is the breakdown of sediment. And then we like to ask questions about how that sediment gets moved or transported some distances. And because we are tying this into the rock cycle, we need to understand that not all rocks weather at the same rate. And I think you understand that now by looking at Bowen's reaction series. So different types of rock contain different types of minerals, and depending on where those minerals lie within Bowen's reaction series, they are going to weather at different rates. And so this is called differential weathering, and that's lots of time is why you see a waterfall, because if you're in the southeast of the United States, lots of times you have these cyclothems or units, packages of rock that are limestone, sandstone, and shale. And so shale, what we know is that shale breaks into really thin pieces and is really easy to break apart, even like with your hands. So that begins to erode first, and that might be underneath a sandstone unit. And the sandstone is really resistant. So what happens is the shale undercuts, gets weathered away by water, and then you have collapse of that sandstone on top. So you end up with these waterfall features as a remnant of what type of rocks are in the location. With specific to our area, we're in the Ridge Valley. Certainly there's a lot of different types of waterfalls, but I want to call your attention to the divide between what's called the Piedmont and the coastal plain. So the Piedmont is an igneous rock. It's crystalline, a crystalline igneous rock majority. And once you cross the fall line, you are into the coastal plain. So you're into sedimentary type of rock. So the crystalline rock is much more resistant to weathering than is the sedimentary rock. And so oftentimes, again, you get a drastic change in gradient that results due to the rock type. And just as you're driving down the road, up or down Highway 75, you might see different packages of rock. And so you can visually see which of those rocks are eroding quicker than the others just by general observation. So in this picture, you see packages of limestone and shale. And again, the shale is the more easily weathered rock. And so you can see how it is lesser than the limestone in these pictures. So what are the factors that are influencing the weathering rates of minerals? And we're going to discuss a few of those. So the first one is the properties of the parent rock and the rate at which they weather. So on the screen, what you see is three of our favorite minerals: biotite, feldspar in the center, and then a rose quartz. We already said that because of Bowen's reaction series, that piece of biotite will weather more quickly. So this is true for any other rock. You would just have to consider which is the weakest mineral within that, and that will erode first. And additionally, we have to consider the susceptibility of rocks to cracking. And what we need to recognize here is that although we don't talk necessarily about cleavage, that was a term that we used when we identified minerals. We don't necessarily use that to describe rocks, but it's a very similar idea in that we're looking to think about how rocks break naturally. So a piece of shale that's on the right-hand side of the screen is going to break into flat plains. So water is going to get on top and below, and it's going to end up in these very flat and platy pieces of rock as it breaks. Granite, however, granite usually breaks in an X formation, and you have to look pretty close to be able to see this, but they fracture on an X and Y plane to produce an X. And so oftentimes, like when people are mining granite and they're putting the dynamite in, you would see these X formations because they're trying just to enhance the natural plane of break. Something like limestone is going to break into a true cubic type shape. So these are all different ideas that's affecting and controlling the rate of fragmentation, because anytime that you have a fracture, you're going to be able to introduce water into the rock. An example on the screen that I like to share is this idea of honeycomb structures. And honeycomb structures are found in sandstone. And oftentimes, if people are interested in rock climbing, they love to find these honeycomb structures because they act as natural handholds. So in the case of a honeycomb structure, it's made out of sediment, like sand-sized particles, but there's also usually larger cobbles, so like quartz pebbles that are intermixed, like a conglomerate is what we would call that, as a type of sedimentary rock. And so the bigger pebbles will begin to weather out, and once they fall out, then water can get in, and the handholds can get bigger and bigger. So this is another type of example of the susceptibility of a rock to weather. The next has to deal with climate, and specifically, we're thinking in terms of rainfall and temperature. So with high temperature and high rainfall, you increase chemical weathering. So the process of perhaps, if we're thinking in terms of a limestone is a sedimentary rock that has calcium and carbonate in it. If you introduce rain to this, maybe like in a tropical climate, rain naturally has a high acidity. So rain is naturally around a pH of 6.5 or 6.7. And so it can chemically break down the rock that's in place. So oftentimes what happens if you're like in a place like the rainforest, maybe in Costa Rica, maybe in Uganda, maybe in Brazil, there's often a really thick soil unit, because when you break down rock, that rock turns into soil as a result of chemical weathering. So because we said that rainfall and temperature are really important in the rate at which bedrock weathers, we can compare three different systems. So we can compare the rainforest, the desert, and the tundra. And this is kind of fun to do because we explained that different energies can be explained by wind, water, and glacial activity. So if we're comparing these for how quickly they are eroding, we would say that the rainforest is the predominant. So it's eroding much more faster, and that's because it has much more rainfall, and it also has temperature, which induces soil activity, which is our third in the list that we're discussing. So when we consider bedrock, and we consider that it's going to be broken down by weathering and then probably eventually transported by erosion, we can look at these boulders in our natural system. So this particular one comes up from the House of Dreams on Mountain Campus. And what we notice is that when we look at these boulders up close, there's something that's growing on them that's called lichen. And so lichen are these circular moss-type features, and lichen that are photosynthetic are going to grow laterally. They're not going to grow vertically. They're going to grow laterally. And so they don't have a vertical root system. They have a lateral root system. But nonetheless, it is those root systems that are taking up energy from that rock. So rocks are composed of minerals, and the organism needs that in order to live and produce photosynthetically. So So it's using the minerals within the rock, and as it's doing that, it is helping to chemically and physically break down the rock into soil. And although we're not going to go into this too much in our physical geology class, we talk a little bit more about this in our geomorphology class. I just want you to recognize that, like looking at the diagram on the right, you can see the parent material. So the parent material is a bedrock, and it remains unweathered. But eventually, that bedrock will begin to break up, and you form these different soil horizons. So starting at the surface, you have the organic layer, followed by an A layer, an E layer, a B layer, and a C layer. And there's going to be great variability on the presence or absence of these layers depending on the bedrock that you initially start with. So soil profiles have great variability, and of course relating to climate, etc. But whatever your bedrock is will determine what your soil is in the area. So as an example, in Georgia, at the coastal plain, the bedrock is a sandstone, and that can break down into soil that's really porous. And so well-drained soils that can be used to grow things like peanuts and cotton, and peaches are another example. So specific types of soil have specific characteristics, and it's all reliant upon the type of bedrock that you have. So different areas of the country produce different types of fruits, vegetables, and agricultural crops because the bedrock is different. And I put this up here just to give you an example of how there's these different soil profiles that we can see. So what we learned is that soil is a product of weathering. The presence of soil encourages weathering process to continue. So it's kind of like a positive feedback cycle. Once you have some soil, you're going to allow for vegetation to root, and vegetation is going to enhance the permeability of the soil, so allowing rain to fall at the surface and to travel in and throughout. And that's going to encourage the bedrock to break down, and the cycle continues. And the next factor is the length of exposure. So asking the question, how long has the rock been exposed to weathering? The longer a rock is exposed to weathering, the greater the chemical alteration, physical breakup, and dissolution. So we can make some comparisons between two different landscapes, a modern volcanic landscape and an ancient volcanic landscape. And without knowing anything else, it's usually pretty quick to determine which one of those has experienced more erosion than the other. So the ability for it to be exposed at the Earth's surface will determine the rate at which it begins to break down. So I like this graph because it summarizes all of what we talked about. So the properties of the parent rock, the climate, the presence or absence of soil, and then the rate of exposure. So ultimately, if you have a mineral component in your rock that is really soluble in water, and it fractures, it's able to fracture, there's a high amount of rainfall, the temperature is really hot, then you're going to produce a very thick layer of soil that probably has a good organic material. And that is kind of like your best case scenario of increasing the rates of weathering and erosion. So that leads us to discuss some generalities about weathering processes. So I mentioned that we can have physical weathering or chemical weathering. So by our definition, physical weathering is the process of breaking rock into smaller units, and the chemical composition doesn't change. So you're breaking large rock into smaller and smaller pieces. So you're thinking maybe a boulder rolls down a hill and now it's into many pieces. And then you take those pieces of sediment and smash it with a hammer. Now you have more pieces of sediment. So the interesting thing is that if you compare a boulder to those tiny pieces of sediment, you have increased the surface area of which they can now be exposed to chemical weathering processes. Examples of physical weathering are going to, again, occur along planes of weaknesses. So we mentioned how granite fractures in an X, shale fractures in parallel layers. Limestone can have jointing, but anytime that you have a fracture or a type of jointing, and especially in areas that receive freeze and thaw cycles, you can end up with a physical weathering process that's called frost wedging. So you're imagining, I mean, you can even see this on the sidewalk. So you're imagining a crack gets infilled with water, and as that water freezes, the volume and space that water took up is going to increase. So now your crack is going to be bigger than what it was initially. And so back and forth with that process, eventually what's going to happen is your rock is physically going to break off. Another example, here's a picture of frost wedging in Antarctica. So you're looking at that boulder and imagining water infilling and then freezing, expanding, and then eventually the rock is going to be broken to pieces. Another thing that can happen is physical weathering that's done by organisms. So, and you can see this even anywhere around campus. And that happens when you have trees that are growing at the Earth's surface, and remembering, like when you see these scenarios that are on the picture, remember that they probably originated as saplings. So you have bedrock and you have a sapling that's growing, but then eventually it grows bigger and bigger, and as it does, its roots begin to spread, and that can physically break down a rock in the natural environment. So activity by organisms, and then the last one that I will just mention to you is called exfoliation. So we're familiar with Stone Mountain, that's just south of the airport in Georgia. So Stone Mountain is a dome, and one of the reasons why it's a dome is because that body of granite is working its way up to the surface through isostatic rebound, and so as it's moving up to the surface, it's giving off pressure, and so that pressure is released by these sheets that you can see, and so it's kind of like sides of an onion that begin to peel off. That can also happen as a result of what's called thermal expansion. So granite has a really high specific heat capacity. It can hold on to heat, but then as it cools, it contracts, and so you get these kind of like micro fractures that happen over time. And that can lead to something also called spheroidal weathering. So if you've seen very round boulders in the natural environment, and you're kind of asked the question, did somebody carve that? Probably not. It's probably a piece of granite that has exfoliated to create that round shape naturally. So then, lastly, I just want to introduce chemical weathering, and by definition, chemical weathering is the dissolution of minerals as a result of chemical reactions. So really what that means at the 101 level is we're looking to see how limestone dissolves as it is exposed to some type of acid. So in lab, what we did is we had a piece of calcite, and we took a very diluted version of acid and put it on it, and we watched it effervesce. So we were watching the chemical reaction on the screen take place. So we saw calcium carbonate and hydrochloric acid produce a carbonic acid and a calcium chloride. And so essentially what's happening when you put the acid onto the calcite, it begins to dissolve and become smaller. And so, that's when we talked about at the beginning of the lecture where you have these limestone tombstones. They dissolve on themselves, and they dissolve by chemical weathering because rainwater is naturally acidic. And so this happens as a positive feedback cycle where physical or mechanical weathering kind of works together. So if you have a boulder, you break that boulder into smaller pieces, you increase the surface area but now the surface areas can be exposed to chemical weathering. And that can just be water, as we mentioned. So water that's naturally acidic can begin to break down the surface area of those smaller and smaller pieces. And so that's a lot of how our landscapes are formed. So what we're going to do in our next and upcoming lectures is, now that we've defined the idea of weathering to be the breakdown physically or chemically of a rock to produce sediment, and we've learned that sediment can be eroded, which means transported to different locations, we're going to learn how that sediment can become a sedimentary rock through the process of lithification or cementation. So how those individual grains can be compacted together to produce a sedimentary rock, like a sandstone as an example. So with a sedimentary rock, you have to have some type of a pre-existing sediment that's broken down into pieces that will eventually become lithified. And then some type of chemical precipitate will be able to act as the glue to hold those together. These are, at least for a clastic type of sedimentary rock. We're also going to introduce bioclastic and evaporite. So I think I will stop here for today. You've been a wonderful audience, and next time you go to the beach, I'm sure you will think of this lecture. Have a great day.